Hello, and welcome to our video, What Caused the Younger Dryas? Produced by the Geology of Climate Change class at Middlebury College. The Younger Dryas is a climate event that took place from about 12.9 to 11.5 thousand years ago. It was first noticed by paleobotanists who noticed the strange advance in retreat of flowers in northern Europe. However, in the mid-90s, the first ice cores were drilled on the Greenland ice cap, shown here. By analyzing isotopes in the layers of this ice, scientists were able to reconstruct temperature fluctuations at a very high resolution over the last 40,000 years in Greenland. What these show are wide swings in temperature, known as Dansgaard-Oeschger cycles. But perhaps one of the biggest temperature crashes came right as the world was starting to pull out of the last glacial period. It got very warm, and then suddenly temperatures plummeted by 8 degrees or more, and stayed cold for more than 1,000 years in this period known as the Younger Dryas. As Earth recovered from the Younger Dryas, we've moved into a relatively stable period of temperature called the Holocene. Around the time of the Younger Dryas, archaeologists have noted that a major type of spearhead called the Clovis point disappears from the archaeological record. Presumably, these spearheads were being made by an ancient Clovis people who were using them to hunt large game in North America in particular. So what happened to these people? Did they disappear? Did they migrate? Did they go extinct? And how does it relate to the Younger Dryas? Around the same time, we see the disappearance of Pleistocene megafauna from the fossil record. These are huge animals that we often associate with glacial periods, such as woolly mammoths, types of ancient horses, Irish elk with huge antlers, and even the woolly rhinoceros. Scientists have noticed that these mega animals had a pulse of extinction right around 12.8 thousand years ago. So this shows time here, and this shows all these species of megafauna that went extinct right around 12.8 thousand years ago at the start of the Younger Dryas. So is that coincidence? Or are all of these things related? Some scientists think that all these things are related and have come up with hypotheses to explain the Younger Dryas cooling episode. The first hypothesis is that glacial outburst floods might have flowed into the North Atlantic Ocean or into the Arctic Ocean, here or here, and actually shut down thermohaline circulation. And thermohaline circulation is basically the idea that warm ocean currents bring warm water into the North Atlantic. As that water cools and is salty, it sinks and is transported back to the south. So this thermohaline oceanic conveyor belt acts to bring warm water into the North Atlantic and return cold water back out. So the idea is that a flood event could have shut down the formation of this deep water and stopped this whole thermohaline conveyor belt, essentially cutting off a source of warm water to the North Atlantic and leading to the big cold spike in the Younger Dryas. And many scientists have looked for these flood events. We know that as the Laurentide ice sheet was retreating, we have a bunch of glacial lakes that were forming right up against the edge of that ice sheet. And we know that as the ice continued to retreat, these lakes occasionally catastrophically drained, dumping fresh water into the North Atlantic, or perhaps dumping fresh water straight into the Arctic Ocean. However, another group of scientists has a competing hypothesis. Their idea is that the temperature drop, the Clovis extinction, and the megafauna disappearance could all be explained by an impact. What if a meteorite or a comet hit Earth and created a lot of dust, which shrouded the Earth in a reflective layer and caused a sudden drop in temperature? Perhaps that meteorite also set off wildfires, which burned across the continents, creating ash, killing animals, and forcing extinction or migration of peoples. So the impact hypothesis was partially motivated by a strange black layer that appears within the sediments at Younger Dryas time. So here we have older sediments, the black layer, and younger sediments sitting above. Could this black layer be filled with debris from a meteorite impact, or with charcoal from rampant wildfires that occurred at Younger Dryas time? Proponents of impact have measured various materials above the layer, in the layer, and also below the layer. For example, they've measured iridium, the presence of magnetic particles, or the presence of glassy carbon. And what they show is that all of these supposed impact markers are relatively low before the Younger Dryas, they spike at Younger Dryas, and then they go back to being low. So they argue that spikes of iridium, spikes of magnetic particles, and spikes of glassy carbon record this impact event in the associated wildfires. However, opponents of the impact hypothesis have strongly argued that there's much more conventional explanation for things like magnetic particles, which, for example, can come from rocks and be rounded and concentrated by wind or by river processes. The same thing with carbon particles or carbonaceous spherules. These don't have to come from wildfires. For example, this 2011 paper pointed out that this carbon spherule, which was attributed to wildfire, actually looks identical to a fungal sclerotium. So are these things really from wildfire, or could they be from naturally occurring soil processes? To explore this debate, we've developed a 10-part video that considers 5 lines of evidence for and against the impact hypothesis. What about outburst floods? Is that plausible? Extraterrestrial materials, carbon materials, the presence of impact layers in ice cores, and a physical record of impact. We hope you enjoy the video. Thanks for listening.
The first piece of evidence in support of a glacial outburst flood causing the Younger Dryas is high oxygen-16 isotope levels in glacial lakes. These levels were studied in foraminiferous sediment cores from the Beaufort Sea. Here, higher O16 levels from the Younger Dryas period, as compared to the surrounding time periods, indicate freshwater floods from glacial lakes. Researchers can compare the delta O18 change in the Beaufort Sea to foraminiferous sediment samples 14,000 years ago in the Gulf of Mexico, a known site of post-glacial flooding via the Mississippi River. The similarity in delta O18 signatures indicates that glaciers were in fact melting and flooding into the Arctic Ocean at the start of the Younger Dryas, and contributed to the freshwater buoyant lid over the North Atlantic, in turn disrupting the North Atlantic deepwater convection cycle and cooling the climate. The second part to the pro-flood argument is that modeling and sediment records support the presence of a massive flood of fresh water from Lake Agassiz to the Arctic Ocean via the Mackenzie River. For years, it was assumed that the path of fresh water to the Atlantic followed the St. Lawrence River, but the evidence for this theory was inconsistent. Modeling work by Condren and Windsor in 2012 confirmed that this route could not explain the disruption of thermohaline circulation in the North Atlantic because ocean currents and the Coriolis effect would deflect fresh water too far south. In comparison, when researchers modeled a mass release of fresh water at the mouth of the Mackenzie River in the Arctic, they found that currents would carry the water into the path of convection points in the North Atlantic and have a much stronger effect on thermohaline circulation, which could have triggered the cooling of the Younger Dryas. Furthermore, luminescence dating of fluvial sediments along the Mackenzie revealed that sediment associated with a widespread flooding event dates to about 13,000 years ago, just before the start of the Younger Dryas. This evidence is significant because prior to this finding, the Mackenzie River route was dismissed because no evidence could be found prior to 9,300 years ago. The work of Murden et al. In 2012 confirmed that the Laurentide ice sheet re-advanced between 11.5 and 9.3 thousand years ago, disrupting much of the earlier evidence of flooding. With this event in mind, the path of flooding along the Mackenzie River 13,000 years ago can be more confidently reconstructed to help explain rapid cooling at the start of the Younger Dryas.
Arguing against glacial outburst floods causing the Younger Dryas. Water is a prime driver of erosion and an excellent transporter of various materials. A flooding event large enough to trigger the Younger Dryas would have been quite substantial, yet there is no geomorphic evidence of significant erosion or transport from hypothetical flooding. Many proponents of the flooding hypothesis point to the idea that Lake Agassiz may have drained out at around the same time as the initiation of the Younger Dryas. However, there is geologic evidence suggesting that more recent flooding events from the very same lake have led to the creation of substantial canyons. For instance, other channels near Rabbit Canyon, pictured, thought to have been carved out by similar deglaciation events, have only been dated back to around 8,400 years. These floods are also thought to have been more minor than the amount of flooding that would be needed to trigger a cooling event as significant as the Younger Dryas, meaning both that it's unlikely that they show evidence of the flooding that is argued by some to have caused the Younger Dryas, and, despite being more minor than the proposed glacial outburst flooding thought by some to have caused the Younger Dryas, they still left geomorphic evidence. Pro-flood researchers also point to a decrease in the O18 isotopic record as evidence for a freshwater inundation causing cooling. However, this shift could have also come from the slowing of the melting process. This slowing occurred just after the beginning of the Younger Dryas, which is essentially indistinguishable in the timing record.
Examining sediments near the Younger Dryas boundary shows clear evidence of materials that could only have been created by extraterrestrial impact. One such extraterrestrial material is nanodiamonds. Nanodiamonds are tiny diamonds that can either arrive inside the impactor itself or can form during the collision with the Earth's surface. They have been used as evidence for other known impact events in the past. They've been found in multiple locations all across the southwestern United States, and all in the same boundary layer shown here in the figure. These three figures, taken from Kennett et al., show the stratigraphy of the Younger Dryas boundary sediments. All three locations demonstrate high concentrations of nanodiamonds at the Younger Dryas boundary layer, and no nanodiamonds are present during any other period. This is strong evidence for the impact hypothesis. Another piece of evidence are magnetic microspherules. Like nanodiamonds, they have been associated with previous extraterrestrial impact events. And similarly, their concentrations also peak in the Younger Dryas boundary layer. Microspherules can also be formed through volcanic activity, but a scanning electron microscope analysis of Younger Dryas boundary microspherules proves that they had non-volcanic origins. So in conclusion, the sediment record shows clear support for the theory that the Younger Dryas period was caused by an extraterrestrial impact event.
Arguments against evidence for extraterrestrial materials in YD-age soils. Dalton et al. 2012 found that there were critical problems with the collection and interpretation of nanodiamond data in previous studies. Nanodiamonds observed in these studies are actually N-diamonds. These cannot be used for an indication of impact because they are easy to confuse with Cu nanocrystals that are already existing in the soil. The image from the right shows nanocrystals from finely crushed carbon sphericals.
Additionally, Pinter et al. Analyzed YDB black mats and compared them to dated sources and sediments of other ages. Pinter et al. Found that YDB age deposits contained identical nanodiamonds and carbon spherules and glassy carbon as older sediments and sediments from modern forest fires. Pinter et al. Discovered that terrestrial materials were interpreted as having ET origin. Table 1 on the right shows all of the sediment layers containing identical nanodiamonds from 4 different sites. The ages of the different layers containing nanodiamonds indicate that YDB-age soils are not the only layers containing nanodiamonds.
In contrast to past evidence, Servell et al. 2009 found that the magnetic grain levels in the YDB samples across North America do not show increased magnetic grain levels in relation to non-YDB soil samples. This is evidence that magnetic grains can come from any array of different sources, and the origin of the grains cannot be assumed to come from an extraterrestrial source. In Figure 1, the YDB samples do not show a peak in magnetic grain level concentrations in YDB layers. Figure 2 shows pictures of magnetic microspherules that have also been discovered in non-Younger Dryas boundary samples.
Arguments for carbon materials representing impact. It is believed that there are two main sources of the carbon materials found within Younger Dryas boundary layers: impact and wildfire. These two sources are related, as it is thought that an impact could have led to widespread wildfires, However, the products of these processes are not always the same. The Younger Dryas boundary layer is a sediment layer that has been observed in multiple locations across the continent and contains above background amounts of magnetic microspherules, iridium, and other impact proxies. It is often overlain by a black mat, as seen in the top right-hand figure. One of the proxies seen in this layer are nanodiamonds, known to form either via shock metamorphism or arrive on an extraterrestrial impactor. The image on the bottom right shows a spike in the diamond concentration within that boundary layer. The nanodiamond polymorph seen within the Younger Dryas boundary layers is known to occur in meteorites. In addition, fullerenes containing extraterrestrial helium were also found in Younger Dryas layers. Fullerenes are those large ball-like carbon allotropes that kind of look like soccer balls. The lack of typical impact evidence such as breccia or huge craters can be explained by the hypothesis that a fragmented impactor created a series of air shocks before hitting the surface, which would result in these impact products. In addition to evidence pointing to impact, the Younger Dryas boundary layer contains evidence for intense wildfires. Some of the evidence found pointing to wildfires includes glass-like carbon several centimeters in diameter, seen within that black mat layer that is often associated with the Younger Dryas boundary layer. Combustion-related aerosols such as ammonium were found in 3 ice cores from Greenland, as visualized in the figure to the right.
There are 3 pieces of evidence that go against the impact theory in terms of carbon materials. The first piece of evidence is that nanodiamonds found within the Younger Dryas sediment do not act like detonation or forest fire synthesized nanodiamonds. This conclusion is shown by this figure. There are also no details on the methodology of how parts per billion concentrations were measured for nanodiamonds found in the Younger Dryas layer. Therefore, the reliability and accuracy of the parts per billion measurements are impossible to evaluate, and it is unclear whether what was found are truly nanodiamonds. Next, glassy carbons do not imply high temperatures. It is suggested that the glassy carbons found may be solidified tars from low temperature charcoalification. High temperature burning of wood showed evidence of physical changes due to heating, but no evidence of vitrification, when something chemically transforms into glass due to heat exposure. This therefore disproves the theory of massive forest fires resulting from meteor impact. Lastly, carbonaceous spheres and elongates do not show signs of extraterrestrial carbon or impact-induced megafires as scientists had previously theorized. They are in fact indistinguishable from fungal sclerotia and arthropod fecal material, which are common of terrestrial deposits.
There's a lot of evidence for the impact hypothesis found in the ice cores from the Greenland ice sheet. Levels of nitrate in the atmosphere at the time of the onset of the Younger Dryas were very high, as indicated by the spike in this graph here. At the same time as this spike in nitrate levels occurred, there was also a spike in ammonium levels, indicated by the spike on this graph here. These high levels of nitrate and ammonium are typically associated with large-scale biomass burning from wildfires that could have caused the Younger Dryas. At the same time as these increased nitrate and ammonium levels, there was also an increase in CO2 levels in the atmosphere, shown in this graph. This CO2 had a very low carbon-13 to carbon-12 ratio, indicated by the decreasing in this graph here. Plants prefer carbon-12 to carbon-13, indicating as well that this increased CO2 came from large-scale biomass burning. Evidence that these wildfires were caused by extraterrestrial impact can be found in the platinum levels in the ice cores at this time. There's evidence that at the onset of the Younger Dryas, there was a lot of dust in the atmosphere that had very high levels of platinum, shown by the spike in this graph here. This increased dust in platinum is usually associated with volcanic eruptions. However, volcanic eruptions are also usually associated with high levels of iridium. As shown by the spike in this graph here, the platinum to iridium levels increased dramatically at the onset of the Younger Dryas, indicating that there was not a large injection of iridium into the atmosphere at the same time as the platinum and that the platinum did not come from volcanic eruptions, and therefore must have come from an extraterrestrial impact that caused a lot of dust in the atmosphere and triggered large-scale wildfires that started the Younger Dryas.
This next section is a counterargument to the previous section, and will discuss reasons that the Greenland ice core data does not support impact hypothesis for the Younger Dryas period. First, the platinum spike seen in the data theorized to have been a result of the impact or explosion actually precedes the ammonium and nitrate spike in the ice core by roughly 30 years, as can be seen in the graph. This would make it unlikely that the source of the platinum is the same source as the biomass burning associated with the ammonium and nitrate. Second, and a more general point, the data that proponents of the ice core impact theory use has never been reproduced by members of the original team or independent research. Several studies have tried and failed to reproduce these results at both the same site and different sites in Greenland. Holliday states that, quote, "This lack of producibility raises serious questions about the appropriateness of the methods to detect the purported indirect indicators, or the laboratory protocols themselves are less than exacting." Two other studies extracted some level of agreement with the ice core data, but showed similar levels of indicators even within the last 40,000 years, showing that this YDB data is not as much of an anomaly as described. To this end, a paper published by Wetke et al. Discussing YDB sites excludes Greenland data entirely, showing that even proponents of the impact theory are turning away from the ice cores.
Arguments for physical evidence of impact. Work by Kier et al. Uncovered the existence of a 31-kilometer wide impact crater beneath Hiawatha Glacier in northwest Greenland, providing support for the theory of Younger Dryas cooling caused by meteor impact. The discovery of this crater was enabled by airborne radar surveys, and evidence suggests the crater was produced by the impact of a meteor roughly a mile in diameter. While the crater must be younger than the 2-million-year-old bedrock it impacted, geomorphic evidence indicates it is almost certainly much, much younger. Jagged peaks at the center of the crater suggest minimal erosion since the crater's formation, indicating it likely formed from an impact less than 100,000 years ago. At the crater site in Greenland, geologists identified grains of shocked quartz in glaciofluvial sediments around the vicinity of the crater, which could provide further evidence for an impact site there associated with the onset of the Younger Dryas period. When quartz is put under extremely high pressures, the pressure causes the mineral to deform, where the internal structure of the quartz can be changed along the crystalline planes, creating planar deformation features or shock lamellae. The only known causes of shocked quartz are extraterrestrial impacts, nuclear explosions, and arguably lightning strikes. They determined the orientations of all the planar deformation features and compared their distribution to those of 10 existing impact areas. As you can see, the distribution at the Greenland site aligns with the known impacts. From topographic evidence, as well as shocked quartz found around the crater, there is physical evidence supporting the hypothesis that the crater found in Greenland comes from the impact that caused the onset of the Younger Dryas.
Hey everyone, so we will be arguing against the hypothesis that there was an extraterrestrial impact approximately 12,800 years ago that would have caused the onset of the Younger Dryas. We believe that there is no physical record of impact, and that the physics of a comet of the necessary size are simply incongruent with the known properties of comets and the Earth's atmosphere. We have two main reasons that are going to debunk the theories that support why there could have been an extraterrestrial impact that we are going to discuss. First is that, as many scientists have proven, there is no physical record of an impact of this magnitude. The Greenland crater discovered was created by a meteorite 1.5 kilometers in diameter, making it way, way too small to have been the impact hypothesized to have triggered the Younger Dryas. An impact/explosion that contained enough energy to cause the Younger Dryas would have required the comet to be 4 kilometers in diameter, almost 3 times the size as this one, making the crater found in Greenland ineligible as evidence that an impact caused the Younger Dryas. Here you can see the crater in Greenland, and it's only 31 kilometers across, and so it's simply too small of a candidate
to be linked to the onset of the Younger Dryas, and it's just not really accurate data pointing in this direction. Our second piece of evidence is about the physics of known comets in the geologic history. So through the analysis of the relationship between past comets and the Earth's atmosphere, calculations show that the probability of a comet of the necessary size striking Earth is incredibly low, less than 1%. So as this shows, this range right here is really low probability of a comet that could potentially be large enough to onset the Younger Dryas. And so the largest asteroid impact expected over 20,000 year interval is a 250 meter impact. And an object larger than 2 kilometers is exceptionally unlikely. So this is showing how unlikely it is that there has even been a comet big enough to onset the Younger Dryas, and that we should focus our energy and attention and research in other directions. Thank you.